So for the last few years, I've been playing around with this idea that I can use static hindrance, a bit of gravity and friction, and have some design principles where I can find out things which are useful. And in this context, I will show you two examples. One I will briefly go through, the other one probably go through in some details. So the premise of the first example is simple. We have a hollow, tilted, rotating cylinder, and in it, what we do is we put in something like two dumbbells. Typically, these are tiny dumbbells, lightweight, about 100 milligrams in weight. And these are tilted, the entire cylinder is tilted at about 10 degrees and is rotating with a glacial speed of about 1 RPM. That's about, it does, in 10 minutes, it does 1 rotation. So that's very slow rotations. And then what you do is, once you do put in these particles, just because of gravity, they go down and one side of it is closed. And then you put on the drive. And as soon as you start rotating it, you can find that these pairs tend to come together and then they start climbing up the potential. So you are climbing up the gravity. Okay, and we find that as you align this, put these particles together, you can actually connect them into two different kinds of chirality. One which is of positive chirality, which goes up. The other, which can also self-assemble to form a negative chirality. A priori, you don't know which one it is, and those will come down. And in the middle, you have one structure which is not chiral, and that doesn't do anything. Basically, comes down and then reforms to either form a positive or a negative chirality. The positive chirality goes up. The negative chirality stays down unless I have something which has an open bottom. Okay. So that was what it was. And what was very important in this particular problem was that you needed, in addition to steric hindrance, so essentially two was very important. One wouldn't have given you the current. You needed two particles. You also needed interlocking, so a cylinder wouldn't have helped you. Kind of a dumbbell in which one dumbbell could lock into the other dumbbell would have helped you. That's how we had this particular problem. And also the frictional anisotropy, which tells you that it has an easy axis of motion and a difficult axis of motion. So if you want to move perpendicular to your to the axis, it's easy because it can roll in that direction. The other axis is stuck because it has to slide in that direction. Now, having done that, when you don't have a proper understanding of something, what you do is you start looking for other examples. And we have been looking for other examples, other toys. And this is another toy that we have. So what we have here is we have two pencils. And these are like, put it in some glass cylinder up here. And you start to shake these things in vertical direction. So I'll show you a particular movie randomly taken. So essentially, you see that these are being shaken and these two things starts to rotate. And if I take one of them out, you'll find that the rotation stops. There's no rotation for one of them. And if I inject it again, the rod, and now you realize the rod has been injected in a different direction, then the thing starts to rotate, but rotates in the opposite direction. So all that you have here is the same simple thing. You have steric hindrance because there are two rods. There is one rod cannot pass through the other rod. You have gravity and you have some drive in the system. And also you have ordering of the system where you mean that there is a yellow and there is a one where there is a taped, another one which is not taped. And if you were to look at the center of mass, then one was ordered before the other. So one came at a higher Z value than the other. Okay. So if you did a very simple-minded experiment analysis of the whole thing, is that you say that, well, I'll take one tip of it, I'll color it red, and I'll basically see that angular displacement as a function of time. Then what you have is you have a thing which moves like this, and you can characterize this thing with terms of the shaker's frequency. I'm doing a vertical shaking, so of shaker's frequency, square of the shaker's frequency, and an amplitude which is A. And if there is one, then basically that's the black line for you. Almost no current in the system. If you have two particles, and for some particular drive frequency, which is actually gamma is equal to 0.81, you have the red. I increase the drive frequency. I go to still higher angular velocities, and then if I do still higher, then suddenly the current drops in, and the reason it drops in is because you have two orientations of the system. You can have this black and the blue and the gray pens, and you realize that the blue and the gray pens are opposite, are different in their arrangements. In the left hand side, you have the blue which is before the gray, and in the right hand picture, you have the blue which is before the gray. So as you start increasing the drive, you can have toggling between the two. One sets that I'm going to have a clockwise direction, the other sets I'm going to have an anti-clockwise direction. So if I start getting toggling into the problem, then on an average, I start getting a zero current in a system. So there are patches in which the thing moves in a clockwise direction. In the next patch, it moves in anti-clockwise direction, so on and so forth. Okay. So you can look at this problem and say, well, there is an energetics into the problem because there is a center of mass and there's a gravity in the problem. And going from one thing to the other, it basically takes you from going from something like this, and you basically have to take it up and then slip it up like that. So if you do this, then there is an energy cost to it, and that energy cost divided by your energy that you're injecting into the system tells you there is a gamma C into the problem, beyond which the drive will not actually help you, and it will actually cause the toggling between the two chiral structures, and you're going to have low currents in the system. And it is what you have. You have an omega versus gamma plot where you have something which goes linear. So essentially your individual currents goes up, two particle current goes up as a function of gamma. So as I'm tweaking up my angular frequency, and beyond a particular point, which is gamma C, it drops it. And gamma C does scale with R by A. So R by A tells you that there are two potential minimas, and I have got a potential energy barrier, and that barrier goes up by R. And if I increase my R, basically the energy barrier is higher, and the particles are more stable in these two configurations, two minimas that you have. And in each minima, it has either a clockwise direction or an anti-clockwise direction motion, depending upon how you define it to be. So what happens if I start adding more particles to the system? If you add more particles to the system, you get some current, but you also get a complicated current because essentially you have shells in which the currents the particles tends to move. If you look on your left-hand side, you have a red point, and you can't really see there is a yellow point somewhere in the system also. And if I were to tag the distance between the two, you would have seen that the distance between the two kind of toggles around a bit. So the two particles' displacements are not fixed. On the other hand, if you had a much larger system, dense system, then these particles will actually tend to move as a robust, one coherent part of a system. Okay. Okay, and what you can do is so let's do this, and then what I do is I actually find when I say now the omega, then omega means the outer shells particle is what I am mentioning it about. So that's my omega, and that tends to go up initially with my phi. So I increase my particle density, and my current tends to go up for the same amount of gamma that I have in my system, and at some point it starts to drop. The reason it could drop is for multiple reasons, but one trivial reason is just because there is a lot of friction in the system, and the friction doesn't allow you to move any further, and that kills your geometry. And if you look at the friction in your system, and you can do this by putting in particle rods into the system as a function of phi, you'll measure that roughly beyond the point at which you start getting the current to come down, which is about 0.6, you basically get somewhere about 0.7, the friction comes up, and then the friction is very large. And if the friction becomes very large, the system gets jammed. Okay. If you have a single particle, your naive expectation would be, well, the particle jumps up and down. So if I have a particle which is tilted much more, then essentially its component in the sliding component is high, and that particle should move more. So you would have expected that if I had a larger density of the particles, each particle cannot slide much, and they're kind of erect, and that's why you should have expected the current to go down. It turns out that it's much more complicated than that, and this simple picture doesn't work out for this particular system. Now, you can do this thing for a large number of systems. It looks like towards the left of the system, that is beyond phi c, for large class, everything collapses and everything is nice. But after phi c, things becomes haywire, and you really don't understand what really is happening, except that all of them shows that the current will actually come down. You can measure something more than that. You can take 2 points in your system and measure the fluctuations of your R and T. If you are at low density, then basically this R fluctuates as a function of time. And if you're at high density, it's like a rigid object. And basically the R is also a constant, and so the correlation function doesn't drop. you extract a time scale out of this correlation function, you will find that the system at phi c that there is a divergence of this time scale. So phi c gives you a rigidity threshold in your system. So there are two modes in your system. Modes in which
Ghosh, you have 2 more minutes.
The modes in which you can actually have things which are rocking around, and things and modes in which things are basically sliding around. And so what you have is there is a soft mode. If you take your system and move from one mode to the other mode. So for example, if you're tilting, you can take the straight bunch of rods like this and tilt it in one direction. So there is a soft mode for tilting that you don't have a current. And on the other hand, the moment the tilting gets blocked by a critical angle, and if you want to drive it any further than that, then you get a sliding in your system. Okay, so let me not do this up. It's also, there's another measure that you can do from here also, that you can extract out a phi c out of the system, and looks at the phi c of rigidity comes at about 0.6. So, so how do you understand the system? Is that the tilting is like you're trying to turn a turntable in which there is a little bit of a hole in the system. The green rod is being turned around, and if the green rod is turned around where the hole is, essentially no force is being exerted to the turntable. The moment the green rod goes and hits along one of the edges of your groove, and then you push it further, then basically the thing will start to turn. Okay. You can actually play around it with slightly more. You can put any magnetic interactions, and the magnetic interaction starts to make the current look still more non-monotonic in nature. You find the current goes up initially, but since the magnetic interactions come into the play, then you have clustering, and once you have clustering and onset of rigidity, the current starts to drop till the point that your drive is large enough that it starts to again pick up, and then you start to get a current again in your system. So conclusions from this particular thing is that the chiral structures can be self-assembled from chiral structures using gravity and steric hindrance. And remember, each of these particles, for example, were not chiral to start off with. You needed anisotropic friction to generate persistent currents in your system. And there is an energy barrier that is associated with the system, and there is a basin of stability in which you can start to play around with it. If you drive it stronger than that, then you will basically come out of the system. So that's what we are playing around with, and we hope that in future there will be many more examples in which we will find out a design principle in which we can use these steric hindrances and get some functionality out of these kinds of very simple-minded objects. Thank you. And I should thank Satyanu Bhadra, the student, graduate student, Shamik Gupta, who worked with me, and Nitin Sure initially worked with me for the first particular problem. Thank you very much.
Thank you, Professor Ghosh, for a very interesting talk. And now the session is open for questions. I anticipate there are no questions.
Mustafa has a question.
Okay,
Shankar,
yeah, Mustafa, please.
Yeah. Okay. No, Shankar, just a very odd thought. I mean, your pencils, yeah, I agree they were chiral, but they were also sort of hard and rigid.
Yes.
I mean, they were very soft objects which could wind around each other or something. I mean, anything interesting there? I mean, each one would have a chirality of its own, and the two of them, that's what I'm thinking. Two sort of springs which interpenetrate or something. I mean, I don't know. I mean, it's just not a very well motivated question, but it just occurred to me.
So yeah, so in this particular problem, the structures themselves were not chiral.
Yes.
And we were looking for a property which came out of the collection of theirs.
Exactly.
You could think about, say for example, screws, for example, putting up two screws together and then driving them together. And if you did so, also at the zeroth order, the effect would be same. But if you have very soft objects, I don't know what will happen. They probably will do much more. They will have internal modes. These don't have internal modes. They don't bend. They don't do things like that.
Mm-hmm. Okay. Yep.
Shriram, please.
Yeah, Shankar, have you thought of considering a much larger array of these? So you actually can look at a kind of a macroscopic phase in which you can get chiral symmetry breaking at the level of many hundreds or thousands of little rods standing up.
Yeah, so
and then you could actually watch that thing coarsening. There is something similar in some old experiments by Kudrolli.
Yeah, so we haven't actually looked at very large systems in this particular thing. We have confined ourselves to basically smaller structures. In most of the other structures, the basic unit was itself chiral. Here, the basic unit itself is not chiral. So once you get a chirality, you basically get the whole thing to have the same kind of chirality. It doesn't, so at least in the experiments that we did, we have not seen it to phase separate into two kinds of chiral structures. So you don't have it doesn't have that a part of it is left chiral and a part of it is moving the other chirality. But that could also be just because we did with much smaller systems.
You might be able to, if you had a large number of little short rods and if you messed around with boundary conditions, you might actually be able to do it. Because without a conserved chiral species, you won't get phase separation of that sort. But you could with boundaries. Anyway, we'll talk. I have some thoughts on this. Thanks.
Okay, if there are no more questions, then we move on. Thanks, Professor Ghosh, once again.